Okay, so we'll start the class now. It's on, isn't it? Okay. We'll start the class now. So, in today's class, we're going to start in a new direction. Okay? So until now in the course, we've been talking about the theory of thermodynamics. This is the theory of how heat is transferred between different bodies, its effects on their temperature, the relationship between heat and work in heat cycles, and so on. Okay? But now we're going to go on to something which initially will look quite different, and this is developing the theory of statistical mechanics. Okay? So it'll be a few weeks before it becomes clear what the connection is between the statistical mechanics I'm talking about now and the thermodynamics I've been talking about in previous weeks. Okay? So at the start it may seem confusing, but just believe that in a few weeks' time you will be able to see the connection between the two. Okay? Okay. Right. So as the name suggests, statistical mechanics is built upon statistics, a statistical analysis of the physical system. And in order to understand statistics, the first thing we need to do is a little bit of a review of probability theory. So what I'm going to do in this class is a brief introduction to probability. So what are the mathematics of probability? Okay, so this will probably take us the next few classes to describe all of the results we need from probability theory to use in statistical mechanics. Okay, so the basic unit in probability theory is something known as a probability space. So I'll define that now. Probability space probability space is the thing I'm defining. Probability space is a set, which for now I will just call X, of possible events and a function which we call P, which goes from subsets of X into the unit interval between 0 and 1. Okay. Such that there are some conditions on this. The first one says that the probability of the whole set, P is the probability function, probability of the whole set is equal to 1. Second thing says, the probability of nothing, that's the empty set, is equal to 0. And if I have two subsets, of X, which are disjoint, then the probability of the union A or B is equal to the sum of the probabilities of A and B. Right. That completes the definition. And there are a few notations and terms here you might not be familiar with, so next I will explain those. Okay, so the things I think you may not be familiar with, firstly, this notation for intervals of the real line. Secondly, what is meant by this, what is meant by disjoint, and then what is meant by this symbol here. Okay, so if you've seen these things before, that's good. If you haven't, then I will just quickly define them. first of all, this interval, right, A and B, this means all the points between A and B. So all points x with A less than or equal to x less than or equal to B. So I draw this on a number line. Here's x, here's A, here's B. Then this notation, square brackets with A and B, means all of those numbers between A and B, all of those numbers in here. So this is necessary here. This P is the probability function, right? P means probability, and when you ask for the probability of something, it's always between 0 and 1. If the probability is 1, that means it definitely happens. If the probability is 0, that means it never happens. So probability is always between 0 and 1. That's what this means. Okay. Okay. Secondly, this thing is the empty set. So this is the set which has no events in it. Okay. Next is, what does it mean to say something is disjoint? And it means that A and B are disjoint if they have none of the same elements. So A and B do not share any elements, any events. So if I give you some examples of this, suppose that I've got a set A, which is the numbers 1, 2, and 3, and I've got the set B, which is 4, 5, and 6, then these are disjoint. Okay? All of the elements are different. However, if I had one set A, which is 1, 2, 3 again, let's say, and I've got another set C, which is 1, 3, 5, then these sets are not disjoint. Right? They're not disjoint because they have some of the same elements. Both sets have 1 and both sets have 3. So finally we come to this symbol, A with the kind of U shape and B. This is called the union. And it simply means the set which contains all of those things of A and all of those things of B. The set of all events in A and B. So using my example here, if I take A union B, then this is all the things in A plus all the things in B. So it's 1, 2, 3, 4, 5, 6. And for example, A union C, as I've defined them here, would be 1, 2, 3, 5. It's the set which contains all of the elements of the two sets. Right. Okay, so I think this example may be a little, this definition may be a little bit abstract, so I want to give you some examples to see why it makes sense. So I'll just start with one simple example. So the example I want to give, which will hopefully make all of this definition clear, is when you roll a dice. Okay, so a dice is this thing, right? It looks, well, you can get them in different shapes, but the standard dice is square, and it has numbers on the side. You must have seen one of these, right? So you often play these in games, you roll it, and you either get a number between 1 and 6. So in this case, the event, what I've called the event here, is just the numbers that you can get on the dice. So the set of the events is the set of possible numbers, which are 1, 2, 3, 4, 5, or 6. So these are all the possible things you can get when you roll a dice. Now, what's the probability? Well, for example, P of 1, this is just the probability that you roll a dice and you get 1. This is the probability to get number 1. Okay? And if the dice is fair, unbiased, so all numbers are equally probable, then this is equal to 1 over 6. Okay, you can get cheating dice where one side is heavier than the other, and then the probabilities would be different. But if we assume this is a fair dice, then all numbers have the same probability, 1 over 6. So you can put other things, for example, this, P1, 2, 3, this is the probability that I get 1 or 2 or 3. Probability to get 1 or 2 or 3. So I roll the dice. What's the probability I either get 1 or 2 or 3? Well, there are 6 possibilities, and this includes 3 of them, and they're all equally likely. So this is a 6 times 3, which is a half. So the probability that you will get either 1 or 2 or 3 is a half. Okay, and this now we can apply to this axiom here. If the sets are disjoint, then the probability of the combination, the union of the sets, is the sum of the probabilities. Right? So what this means is, for example, here, I can write this as the probability of getting 1 plus the probability of getting 2 or 3. The probability of getting 1 is a sixth. The probability of getting 2 or 3 is 2/6, which is a third. And the probability of getting 1 or 2 or 3 is a sixth plus a third, which is a half. So you add probabilities. The probability of A or B is the probability of A plus the probability of B. So this is the sense of this number 2 here. It's saying that you can add probabilities together. You can also make sense of this number 1 as well. P of x equals 1. Well, in the case of the dice then, P of x equals 1 is telling us that probability 1, 2, 3, 4, 5, 6 is equal to 1. In other words, you must get something. Probability equals 1 means it's certain. So when you roll a dice, you must get a number between 1 and 6. So what this axiom Px equals 1 is telling you is that the set X includes all of the things that can possibly happen. Okay? So when you roll a dice, you can get one of these results, but there are no more results. These are all of the possible results. Okay? The set X includes all of the things which could possibly happen. Right, so that's an example, and hopefully that makes the definition a bit clearer. Okay. Now you notice that the way I define probability is it works on a subset. So you give me a subset of this set X, and I can give you a probability for it. But using this axiom about the sums of probabilities, I can always break it down into the probabilities of single elements. Right? So because of this axiom about adding probabilities together, if you give me a finite subset, I can always write it down as a sum of the probabilities of individual events. So, in the case that X is finite, so it doesn't have infinitely many elements in that case. If X is finite, then the probability function P, and let's say that X here then is the set X1, X2, Xn. If this is finite, then the probability P is completely specified by the probabilities of each element. So in other words, by probability of X1, probability of X2, probability N. Okay. So if the set is finite, it's very simple. Okay, it's just as long as you know the probability of each event, that defines everything. But we can also define probabilities on infinite sets, so on sets with infinite numbers of elements. And in particular, we're going to be interested in the case where X is continuous. X is a continuous set of real numbers So for example, X is an interval on the real line. Then we define P, the probability, in a slightly different way. We can do it using what's called a probability density function. P is defined. Probability density function, which I will give the symbol little p. Okay? So hopefully my writing is clear enough to distinguish between big P, which is the probability, and this little p, which is a probability density function. Let me define what is meant by the probability density function. It says the probability that I get a result somewhere between x and x plus a little bit, the x should be equal to the probability function at that point times delta x. So I can draw a picture of this to hopefully make it clearer. Here is p of x, function of x. And we suppose it looks something like this. And if I take some point here, here is x. And I take a very small interval around this point of width delta x. This point here, width here is delta x. Then the probability of getting a number between these two values is equal to the area here. So we can expand this to a general interval. If the 2 points A and B are not close together, so say I take A here and B there, then the probability of getting a number between A and B is the total area here. So the total area there is defined by an integral. It's the integral from a to b, p of x dx. Okay. Now you note that the condition that p of x equals 1, p of x in this case just becomes the integral over x of little p of x dx. So this must be equal to 1. Now there are two very important concepts in probability, which are known as the mean and the variance. Which I guess you must have seen before, but let me define them for you anyway. Okay. So given any function f of x, we can define the expectation which is written in this way, f of x and we have to give two different definitions for the case of a finite space or, well, a discrete space or a continuous space. If the space is discrete, then you just sum up over all the possible events of the value of the function times the probability of the event. And in the case of a continuous one, you have to integrate x. Sorry, this is big P. Okay, so what this expectation gives you is a kind of measure of the likely value of f of x. So if we go back to the case of our dice, x can take any values between 1 to 6. And if I take the simplest case where f of x is just equal to x, then this expectation tells you what is the likely value of x, somewhere in the middle. So you can get a 1, or 2, or 3, or 4, or 5, or a 6. So on average, you will get something like 3.5 in the middle. So that's what this tells you, the kind of average value. Now, in terms of this expectation, we can define the mean and variance. So the mean, which is usually given the symbol mu x, is defined as the expectation of the variable x. So mu x is just the expectation of x, which is these two cases, the sum in the case of a finite set, x times p of x, or the integral in the case of a continuous set, x. Again, so as always, this one is discrete. This one is continuous. So I'll do some examples of this in a minute. First, let me define the variance. Which I will give. There's a variety of different symbols. You can either write it like this, or another notation we'll use is sigma squared. Is defined as the expectation of the distance from the mean. So variance of x is the expectation of x minus mu x squared. in the discrete case, this becomes sum upon x of x minus mu x squared times p of x. In the continuous case, this is just the integral x minus mu of x squared times little p of x dx. Okay, so that's the definition. These things have quite a simple meaning if I consider a continuous case. I've got some probability function of something like this, say. Okay. Then the mean, mu, tells me a number somewhere in the middle. So it tells me roughly where the center of this distribution is. So for example, for this one, it might be somewhere here. Tells you where the center of the distribution is. The variance tells you how wide the distribution is. You can see here, if I consider two different distributions, this one or one which has a similar mean, but is very tight around that mean, then when you compute the variance is the square of the difference between x and the mean. Okay? So in the case of this distribution, all of the x's are very close to the mean. Right? So x minus mu is always small. So the variance is small. Right? So this one has small variance. Whereas in this one, the distance from the mean can be quite large. Right? You can go quite a long way from the mean. So this one has a large variance. So the variance, as you can see, has units of distance squared. So if I take the square root of that, I get something of units distance. And that is a guide to the width of the distribution here. Something like this. Roughly the width of the distribution is of the order of the square root of the variance. Or, given the symbol I gave it, sigma. So sigma is a measure of the width of the distribution. If the variance is large, that means the distribution is wide. And if the variance is small, that means the distribution is narrow. I defined the variance like this, but you can actually get a simpler formula for it from the following argument. If I just look at the discrete case, the continuous case is the same. This is equal to the sum on x in x of x minus mu x squared times p of x. Well, I can expand the square here, right? So I can write it down as separate terms. So first of all, we get sum upon x in x of x squared times p of x. X squared. Then I get minus 2 times mu times x. But mu is a constant, so I can take that out. So this is minus 2 mu times the sum upon x p of x. And then finally, I get plus mu squared times the sum upon x p of x. So all I've done there is expanded the square. But now we can ask what are each of these terms. This one, let's start from the end and go backwards. This is the sum upon the probabilities over all of the set. And I've already told you this must be equal to 1. Right? If you sum up the probabilities over the whole set, then the answer you get is 1. This thing here is the definition I gave of the mean. This is just the mean mu x. And finally, this thing here is the expectation of x squared. So therefore I can write the variance of x is equal to the expectation of x squared, that's the first term, then I get minus 2 mu squared plus mu squared, so one of them cancels and I get minus mu squared. So I define the variance in this way, but we've shown that it's equal to this. It's the expectation of x squared minus the mean squared. Right, so again, that's quite a lot of abstract definition, so to give you some idea of this, I'm going to do some examples. And the last two questions on the quiz this week are about calculating mean and variance. Okay, so you have to do something similar to the examples. So the two examples I'm going to do are the same as the ones I just did previously. So the first one is x equals 0 or 1. P of 0 is 1 minus p. P of 1 is p. So this is the one trial with success at probability being p. Okay. So firstly, the mean. What's the mean of this? It's the sum x is either equal to 0 or 1 of x times the probability of x. Well, when x is 0, I get 0 times 1 minus p. When x is 1, I get 1 times p. So that's very simple. The mean is just equal to p. Okay. You can also ask what's the variance. So okay, so I'll calculate the variance using the original definition, I think this one. So the variance of x is the sum x goes from 0 to 1 of x minus the mean, but we've worked out that the mean is p times p of x squared. It's x minus mu, but the mu is equal to p, we've just calculated, so it's this. So when x is 0, this is going to be p squared, and the probability of 0 is 1 minus p. When x is 1, this gives me 1 minus p squared. The probability of 1 is just p. So we get this. And this simplifies. I can take out a common factor of p times 1 minus p. And here I get p plus 1 minus p here. This gives me 1. So I get, therefore, the variance is p times 1 minus p. Okay, and then let me just do the same thing for the continuous example I gave. X is from 0 to 1, and the probability density is just equal to 2x. So it looks like this. First of all, if we calculate the mean, mu of x is defined as the integral from 0 to 1 of x times p of x dx. That's the definition of the mean. Then p of x is 2x, so this is the integral from 0 to 1 of 2x squared dx. 2x squared integrates to 2/3 x cubed between 0 and 1. And you evaluate this and you find that therefore the mean. You evaluate this and you find that therefore the mean is 2/3. We're running out of time, so I've got to be a little bit fast, but let's also compute the variance. So for this, I'll use the definition that I proved just a minute ago. It's the expectation of x squared, which is this, minus the mean squared. So here we get 2x cubed dx, and the mean is 2/3 squared. So if I integrate this, this gives me a half x to the 4 between 0 and 1, and this is 4/9. This is a half minus 4/9, which is 1/18. Sigma is the square root of the variance, which, if you calculate it, comes out as about 0.24. So as I said, we can interpret this as saying that the mean is somewhere near the center of the distribution 2/3, and then the variance is something like the width.